Tautomerism, and this is one of the very important isomerism. We had done different type of structural isomerisms, and we left tautomerism for the end, and now is the day when we are starting this. So let's start. What exactly is the tautomerism? Let's understand and how to solve the questions of different types of this category. So tautomerism is a kind of isomerism which looks like a functional isomerism, because here you will see there is a change in the functional group happening for the same function, for the same molecular formula, but it is not categorized under the functional isomerism. Here the most common compounds where the tautomerism is visible is keto compounds, where you have the carbonyl groups present, and these groups gets converted into enol. The first time when this tautomerism was observed in a molecule, that was a keto molecule, and it was getting converted into enol, and this was observed by the scientist. This specific keto compound was observed and was seen that it is in equilibrium with the enol compound, and that's how the tautomerism concept's origination happened. Okay. In this molecule, they saw that another compound is also there in the equilibrium mixture. This is, if you see here carefully, here you have one carbonyl group, C double bond O, and next to it is CH2, and then you have an ester group, right? This is the compound what we have, and this gets converted into, this carbonyl group gets converted into alcohol, and the double bond which is present in the carbonyl carbon, that gets shifted to the carbonyl carbon and the next carbon. So basically the carbonyl carbon and the next carbon carries a double bond, and this ketone's oxygen becomes OH. So this was first observed. From here the concept of tautomerism was started, and scientists tried to figure out that what exactly is happening over here, and then we found this kind of equilibrium getting formed in many other compounds, and then it was made into a different category which is now known as tautomerism. So tautomerism is where a compound exists in two different forms, okay, which are interconvertible. So basically both the forms remain in equilibrium, and here it's like both the compounds exist in the same mixture, in the same compound mixture. Okay, so it's not like functional isomerism. Functional isomerism, you have a molecular formula, and that formula can represent multiple different functional groups, but those will not be interconvertible into each other. So basically your ketones molecular formula can represent an aldehyde also, but that doesn't mean that the ketone is interconvertible into aldehyde. So functional isomers are the isomers which possess the same molecular formula but independently different functional groups which are not interconvertible into each other. They exist independently, right? Whereas tautomerism is the phenomena where a compound exists in two different forms which are interconvertible into each other, and both the forms remain in the equilibrium, and these structures are called as tautomers. So what is the major difference between tautomerism and functional isomerism? In both the cases, your molecular formula represents two different or more than two different type of compounds. In your tautomerism, it is basically the molecular formula which is representing two different compounds, whereas in the functional isomerism, a molecular formula may represent two or more than two different compounds carrying different functional groups. But in the tautomerism, the compounds exist in two different forms together. So basically they are interconvertible and they exist in the equilibrium, so they both exist together. Whereas in functional isomerism, whatever different functional groups your molecular formula can represent, those compounds exist independently and these are not interconvertible. So this is the major difference between tautomerism and functional isomerism. Now, tautomerism, how does it arises? It arises due to the shift of an atom or ion from one position to another, and resonance takes place. Now let's understand. If I have written a compound like CH3, C double bond O and H, this is my compound. I can write it as C with the hydrogens over here, C double bond O and H. This is a compound. Now, as I mentioned, tautomerism arises due to shift of an atom. So what does exactly means? An atom will shift from its position from one position to another. So this is my carbon 1 let's number it like this. This is my carbon 1, this is my carbon 2, this is oxygen. Okay, this is the oxygen. Now hydrogen will break its bond from carbon 1 and will go and shift and will attach to the oxygen of carbon 2. So basically it will make the bond with oxygen, and at the same time oxygen will break its pi bond and the carbon 1 and carbon 2 will form the pi bond. So basically the pi bond will break and a new pi bond between carbon 1 and carbon 2 will form. So kind of resonance is happening. Just look at it, what exactly is happening once again. So here is my hydrogen. We call these hydrogens as alpha hydrogens also. Alpha hydrogens are the hydrogens which are present on the alpha carbon, and these are also called as tautomerizable hydrogens. So these are the hydrogens which will participate in the tautomerism. These are the alpha hydrogens. So what exactly is going to happen? This alpha hydrogen will break its bond with the carbon, and this oxygen's double bond will break and a new double bond will form. So basically you can also say that this pi bond will shift over here and this hydrogen will shift over here. So basically exchange of a double bond and pi bond is happening. The exchange of a double bond and hydrogen is happening. So pi bond of carbonyl group will shift to alpha carbon and the carbonyl carbon, and the hydrogen, alpha hydrogen, will shift from its position to carbonyl's oxygen. This is what happens in tautomerism. So shift is happening over here of hydrogen, and double bond is also shifting. So this is kind of resonance is happening. Resonance means it can go to and fro. This will convert into this. So this will become CH2 double bond COH and hydrogen. So this will convert into this, and again the same process will happen. This hydrogen will again shift back to this carbon and double bond will shift back to the oxygen. So this to and fro kind of movement of pi bond and hydrogen is something which is resonance, and this is what is happening in the tautomerism. We also call this as a phototrophy. This phenomena of tautomerism is also called as phototrophy. Though we will understand this tautomerism in much more detail, and we will see the mechanism of it, how it is happening for different compounds. Here you have to understand alpha hydrogen is shifting and attaching to C double bond O's oxygen, and pi bond is shifting between alpha carbon and carbonyl. I just don't have any space over here, so I'll just write it over here. Is shifting between alpha carbon and carbonyl carbon. So this is what is happening. Alpha hydrogen is shifting from its position going to carbonyl's oxygen, and the pi bond is shifting from carbonyl group or from carbon oxygen to alpha carbon and the carbonyl's carbon. So this is exactly is happening in the tautomerism. So now we have got it. The tautomerism is different from functional isomerism or functional isomers. The tautomers are different from functional isomers, and these are interconvertible and remain in the equilibrium. So they exist together in the equilibrium. Okay, these are not independent structures, they are interconvertible. And as I said that it is like, which is mostly I think I have missed writing here, which is mostly like resonance. So basically tautomerism is similar to resonance but not exactly resonance. So what is the difference between tautomerism and resonance? In tautomerism, all the structures which are forming are real and can be deducted. That means if I say that this is the aldehyde which I had taken, this is also real, and if the compound which I see over here, this is enol, basically you have a OH and double bond, this is also real. So both of these compounds are real and can be detected and can be separated from each other, whereas resonating structures are imaginary. Both of these structures in tautomerism remains in equilibrium and are interconvertible to each other. Resonating structures are also interconvertible to each other, but you cannot separate them out. So you cannot take them out and say this is my resonating structure 1 and this compound is a resonating structure 2. Hence we say that these resonating structures are imaginary. They are interconvertible, but imaginary, only resonance hybrid is real. Now let's see a few more differences. In case of tautomerism, pi bond and sigma bond both participates. How? I have just now shown you that the sigma bond, that means the bond between alpha carbon and alpha hydrogen is breaking, and this hydrogen is going and attaching on the oxygen, whereas the new pi bond is forming between alpha carbon and the carbonyl carbon. So basically sigma bond is also involved and the pi bond is also involved, whereas when we talk about resonance, there is no concept of involvement of sigma bond. It's only and only your pi electrons or pi bonds. Next is nuclear shift possible. Nuclear shift possible means atom shift possible. That means hydrogen atom is shifting its position from one position to another. So that shift is possible in case of tautomerism, whereas in case of resonance, it's purely strictly the movement of pi electrons. It has nothing to do with the atom. Atoms cannot shift from one position to another. So atom shifting is not possible in case of resonance. Now let's understand what all different type of tautomerisms we have. First type of tautomerism, and the most common one and the most asked one, is the keto-enol tautomerism. What do we mean by keto-enol? That means a carbonyl group will get converted into enol group. So basically here is my this keto group. You can call it as a carbonyl group also. So this carbonyl group will get converted into enol. How exactly? I have shown you just now a few minutes back that the hydrogen from here will shift to the oxygen and pi bond will shift over here. So basically double bond will come over here and double bond O, carbonyl double bond O, will get converted into alcohol. So this is your keto-enol shift and they get converted into each other. Next kind of tautomerism is cyanoenamine tautomerism. So cyanoenamine tautomerism means you have a cyano group, that is C triple bond N. So here again we will have a quick look on it. So this is my C triple bond N, this is my alpha carbon, and these are the alpha hydrogens. Now what kind of shift happens? This alpha hydrogen shifts from its position to nitrogen. Okay, so this sigma bond breaks and one of the pi bond shifts between carbon and carbon. Very, very, very similar to keto. Only difference is there is a triple bond between carbon and nitrogen, and instead of oxygen there is nitrogen. It is very similar to keto. So pi bond is shifting between alpha carbon and the nitrile carbon, and the hydrogen is shifting from the alpha carbon to the nitrogen. And this group which is forming is C double bond N, and this is called as enamine group. Okay. Next is enamine, tauto. So the names are very, very confusing. It is enamine, tauto. This group is enamine, where you have carbon double bond NH. Now look at it again very, very carefully how this is going to happen. So these are hydrogens over here. Again the same thing will happen. This hydrogen will go and shift and go to the nitrogen, whereas this double bond will shift between carbon and carbon. Exactly, this is the thing which is happening everywhere, right? And this will convert into CH2 double bond CnH2. So enamine is nothing else but, like, if I have to write the name of this compound, how will I write? How many carbons are there? 2 carbons. So it is eth. Because there is a double bond, it will be ethane, and because there is NH2, it will be amine. So enamine is nothing else but double bond with amine group. And unamine means you have single molecule. Let me just write the name of it. This is 1 2 carbons, so ethane imine. This is my unamine group. So unamine group is getting converted into enamine group. Okay. Next type of tautomerism what we have is nitroso-oxime tauto. So what is nitroso group? Nitroso group is N double bond O. Again, exactly same thing is going to happen. Hydrogen is going to shift on the oxygen and pi bond is going to shift over here. So pi bond will come between carbon double bond nitrogen. So basically will come between carbon and nitrogen, and hydrogen will shift on the oxygen. So this will give you CH2 double bond NOH, and this is your oxime group. We already know this, and this is your nitroso. So in all the cases what we have seen, alpha hydrogen will shift from its position, will go to the atom carrying the pi bond, basically the group which is carrying the pi bond, the functional group's heteroatom it will go to, and then the pi bond will shift from there to alpha carbon. So this is how exactly the tautomerism takes place. Now we will understand so now we have understood these are the alpha hydrogens which are participating in the resonance. These are also called as enolizable hydrogen, basically the hydrogens which can participate in the tautomerism. And to be more precise, as I mentioned earlier also, that keto-enol tautomerism is the one which we majorly use, which we majorly talk about, and hence the hydrogen which can participate in the conversion of keto to enol are called as enolizable hydrogen. But I think you should more widely called as tautomerizable hydrogen. So what is tautomerizable hydrogen? The hydrogen which participates in not enolization, in tautomerization. What is that carbon? What is that hydrogen? Basically alpha hydrogen, or you can say sp3 carbons hydrogen, which is the neighbor of minus m group. So you have a carbon over here which is sp3 carbon, it has a hydrogen over here, and here is your minus m group present. So this carbon, you can also call it as alpha carbon, and these hydrogens also can be called as alpha hydrogens, which should be the neighbor of minus m group. As I mentioned, it is either in this structure, and this sp3 carbon should be neighbor of minus m group, and that minus m group can be an aldehyde, can be a ketone, can be nitroso, can be nitro, can be nitrile, and can be NH. Multiple different, I mean, I have just mentioned 4 different kind of tautomerism. There are multiple different type of tautomerisms what we can do. Okay, so we are doing only 4, and out of these 4 also only keto-enol is something which is very, very important. Okay, and we'll be talking about that in much more detail. Many cases, and where a compound can be tautomerized into enol, where the enol form is more stable, where the keto form is more stable. So all that we will understand. So here I've just listed few types of tautomerism, but there are few more which are there, and the different kind of functional groups which can participate in tautomerism. So basically, that is what we are trying to understand over here, that any hydrogen, alpha hydrogen, which is neighbor of minus m group. What minus m groups we are talking about? We are talking about aldehyde, ketone, nitroso, nitro, cyanide, N double bond NH. These all groups, if they are present, and then alpha carbon have the alpha hydrogen, that hydrogen will be called as enolizable or tautomerizable hydrogen. So now we have got, basically in some simple terms, alpha hydrogen is the enolizable hydrogen. Now I'll give you some compounds. We will see how many enolizable or tautomerizable hydrogens are present in each compound. So just now I have told you what are the enolizable or tautomerizable hydrogens. The alpha carbons hydrogens are enolizable or tautomerizable hydrogen. But there is one more condition where you can consider the hydrogen as enolizable or tautomerizable if the carbon is not directly attached to the minus m group but is in conjugation with minus m group. That means it is in distance relationship with the minus m group through the conjugation, then also the hydrogen will be considered as enolizable hydrogen. This is important, please understand this carefully. Now look at this example what I have given over here. What I have mentioned here is I have C double bond O, okay, and assume the R which is here doesn't have or let's not write R over here, let's write H over here. Okay, so let's say this is my aldehyde. Look at the neighboring carbon. These carbons don't have these carbons are not called as alpha carbons. These are alkenes, and alkenes are not alpha carbons. These we require the hydrogen of an sp3 hybridized carbon. This is sp2 carbon. This is sp2 carbon. Correct. So these hydrogens are not enolizable hydrogens. Look at the next carbon. Next carbon is sp3. I have sp3 carbon, but it is not the neighbor of minus m group. But look at the structure of this whole compound. I have sp3 carbon which has a hydrogen on it, but it is not neighbor of the minus m group, but it is in conjugation with the minus m group. What do I mean by conjugation? Hydrogen single bond, double bond, single bond, double bond. So what is the conjugation means? Single bond, double bond, single bond, double bond, single bond, double bond type of relation. So hydrogen or this carbon is in conjugation with the C double bond O, or you can say this sp3 carbon is in conjugation with this C double bond O, because there is an alternate single double bond is there. So through resonance or through some way this hydrogen can be removed, and we can show the tautomerism over here. How exactly? I will show you. Look at this. So I have this molecule, assume there are hydrogens over here, and then you have CH double bond CH C double bond O and H. This is the molecule, right? Now, what exactly used to happen in case of tautomerization? This hydrogen used to shift from its position, and the pi bond used to shift between carbon and carbon. But that kind of shift is not possible because this is your sp3 carbon and this is your minus M group. So here the process will take place through resonance. Now, what do you mean by resonance? This carbon hydrogen bond will break. This carbon hydrogen bond will break. This hydrogen will come out as H plus. This carbon will become negative. When this carbon will become negative, what exactly is gonna happen? This pi bond is gonna shift over here, over here. So basically, this carbon will, the pi bond will break in such a way that this carbon will gain a positive charge, this carbon will gain a negative charge, and this bond will also break in such a way that oxygen will carry a negative charge and carbon will carry a positive charge. Please understand this. This is not how we should write it, but this is how exactly I have to write to explain you. The bond between carbon and hydrogen is broken. This is broken, and the carbon has become negative. H has come out as H plus. Now the pi bond will break in such a way that in such a way that this carbon will become negative, this carbon will become positive. Now this negative and positive carbon will form a pi bond, so these charges will be gone. Okay, now this carbon has got a negative charge. At the same time, the carbon oxygen, this carbon this oxygen bond will break in such a way that oxygen will carry a negative charge and the pi bond will be gone. So here the pi bond is gone, and there is a negative charge on this carbon, positive on this carbon, so these will form a pi bond. So pi bond is formed, and here also negative and positive is gone, right? What is left in the system? H plus is left and O minus is left. This H plus will go and attach over here, and eventually the molecule will become, we had a compound, we had this compound, let me just write it. So we had compound this CH H H, single bond CH, double bond CH, C double bond O and H. It got converted into CH2 double bond CH, single bond CH, double bond C O H and H. So this aldehydic group has got converted into enol due to the presence of this enolizable hydrogen, which is present at a distance but is in the conjugation. But this hydrogen is in conjugation with this double bond. So basically it is single bond, double bond, single bond, double bond conjugation. Single, double, and that's how this hydrogen could travel from this position to this position. So we can call it as resonance also. And due to this resonating effect, this hydrogen could get attached on this oxygen and could give you this enol. So this is called as distant tautomerism. Okay, so even in such cases, we will consider these hydrogens as the enolizable hydrogens. Okay, but the condition is that enolizable hydrogens or the enolizable hydrogen should be present on the carbon, which is in conjugation with the minus M group. I hope you would have understood. Now let's quickly see how many enolizable hydrogens are present in these structures. So look at this first one. No enolizable hydrogen because no alpha carbon over here. Here this is the alpha carbon, 3 hydrogens are there, so 3 enolizable hydrogens. This is my minus M group, this is alpha carbon, this is alpha carbon, total 6 alpha hydrogens which are enolizable. This is alpha carbon, 2 hydrogens here which are enolizable. Look at this condition now. It is very similar to what we have discussed just now. This is my aldehyde, this is carbon double bond carbon, and this is CH3. So directly there is no alpha carbon next to the CHO, but it is in conjugation with CH3. So I have the exact same thing. I have hydrogen, hydrogen, hydrogen with CH, double bond CH, C double bond OH. So this hydrogen or this carbon is in conjugation with this C double bond O, and hence there are 3 enolizable hydrogens. Next is benzene with CHO. So in benzene, do we have any enolizable hydrogen? Let's see. So this is the structure. There is no sp3 carbon neighbor of it. So no sp3 carbon means no enolizable hydrogen. So 0 enolizable hydrogen in case of 6th. Next is benzene, methyl and CO. Benzene doesn't have any sp3 carbon, so it cannot give you any enolizable hydrogen. This is methyl, it will have 3 hydrogens, so 3 enolizable hydrogens. 2 benzenes, no sp3 carbon, 0 enolizable hydrogen. one benzene, and then C double bond O, and then CH2 CH3. So alpha carbon is this. So alpha hydrogens are 2, so 2 enolizable hydrogens. Look at this. There are one alpha carbon here, one alpha carbon here, total 5 enolizable hydrogens. Look at this, C double bond O, 2 here, so total 4. Look at the C double bond O. Again, we have to look for the conjugation, and see, this is your alpha carbon. This will show, give, its 3 hydrogens will give the enolizable hydrogens. I mean, this carbon will give 3 enolizable hydrogen. Look at this carbon also, which is in conjugation with the C double bond O, and can give these 3 hydrogens. So 3 hydrogens from here and 3 from here, so total 6 enolizable hydrogens. Now look at this question number 13. One carbon here, so 2 hydrogens here, 2 hydrogens here, so total 4 enolizable hydrogens. Now try out these and note them down, try these out on your own, and then I'll discuss the answers. Now note these ones also, and then all together I'll discuss all the answers. So let's discuss now. So 8 and this, how 8, this, so 2 hydrogens here, these are all alpha carbons, hydrogens are alpha hydrogens. So this is 8 carbons here, 8 hydrogens here, 4 in this case, 6 in this case, 0 in this case, 0 here. Why 0 here? Though it looks like there is a hydrogen over here, but this is a hydrogen on bridge carbon, and bridge carbons hydrogen does not participate in tautomerization. Why? Because of the Bread's rule. Why? What is Bread's rule? When this hydrogen will go, there will be a charge on this carbon, and the carbons, and that will be a negative charge, and this carbon will become sp2 hybridized after forming a pi bond. So basically this will become like this. There will be a double bond here and then OH. So basically this bridge carbon will form a pi bond, so it will become sp2 hybridized, which will make this carbon or this structure further unstable. So bridge head carbon can never be an sp2 hybridized carbon. Okay. So Bread's rule say, what is I'll just write it. This is BREDT hyphen S. This is your Bread's rule. Bread's rule says that your bridge carbon can never be sp2. If it is sp2, the molecule will become highly unstable, and the system will disintegrate, will break down, or the bonds will break, and the system will not remain as we are expecting. So that is why this hydrogen cannot be taken out. Otherwise the molecule will become the bridge carbon will become sp2, which will make the molecule highly unstable. Okay, now look at this one again. This is sp3, this is your alpha carbon, this is your alpha carbon. This hydrogen is non-enolizable, this is the enolizable hydrogen, so 1 here. Now in this case 4, how 4? 2 from here and 2 from here, these two and these two. This is, and the distant position, this is alpha carbon, and this is the hydrogens of the distant position, which are in conjugation with C double bond O, hence can participate in the tautomerization. Here there are two hydrogens from here, these are again distant and in conjugation. Next, here there is only one hydrogen here, which is distant but in conjugation. Here there are no hydrogens which can participate in the hyperconjugation. So here there is one enolizable hydrogen. Here is the enolizable hydrogen which is distant and in conjugation with the C double bond O. Exactly same way, here is one enolizable hydrogen. This is not sp3 carbon but sp3 nitrogen, and the hydrogen present here is also enolizable hydrogen. Look at this, there is enol here, and this hydrogen of OH will participate in formation of keto. So already this is an enol system, and it will get converted into keto. So this is one hydrogen which will participate in the keto-enol tautomerism. Look at this. Here there is a CHO, and here you have CH3. How will we write it? This is 3 hydrogens over here, So CH3, this CH3's three hydrogens are in conjugation with this double bond and then this CHO. So these three hydrogens are distant but in conjugation with C double bond O, hence three hydrogens are the ones which are enolizable hydrogens. So that's how we identify that whether the tautomerization is possible in a system or not, and if it is possible, then which all hydrogens can participate in the tautomerization. So here in today's lecture, we had understood what is tautomerization, what are different type of tautomerization we can do. Majorly, we'll talk about ketoenol and which kind of systems can have the tautomerization, which all hydrogens will participate, what is enolizable hydrogen or tautomerizable hydrogen. In next class, we'll talk about the conditions of ketoenol tautomerism and how does the reaction or how does the ketoenol tautomerism takes place in basic medium, in acidic medium, what is the mechanism of it, and then we will talk about stability of enol. That means, as I mentioned, that keto and enol both remain in equilibrium and they are interconvertible in each other, but that doesn't mean that the percentage of keto and enol both products are same in a mixture. The percentage will vary, and percentage will vary depending upon the stability of the molecule. If keto is more stable form, then the percentage of keto will be more as compared to enol, and if enol is stable, then the percentage of enol will be more than keto. So this is all we will be doing in the next class. So till then, go through it. Ask me if you have any doubt over here. In next class, as I mentioned, we will be talking about mechanism of ketoenol and the percentage calculation or to figure out the stability of different type of ketos and enols.